So you see, when it comes to so the remaining parts that are left that we have to discuss, which is technically K and Q, which is related to delta G. And then there's like a special type of question, which is actually pretty interesting. And it's related to organic chemistry that you will do later, which has to do about flipping of the chair conformations, which is we'll discuss later. I mean, not today though, of course, but maybe in 2 weeks or something. And then we'll do Van Hoff, and then we can move on to kinetics, which is pretty interesting. And it's very short though. Like we might be able to finish kinetics by next session. Yeah, it's short, but it doesn't mean it doesn't require practice. But yeah, the organic chemistry part is going to require a lot of time because we're going to cover like so many different topics in organic chemistry, and it's super cumulative. So you need to, yeah, and then practicing is going to be the key. And I think, have you bought the huge booklet that is for practice?
Booklet?
Usually organic, usually like it's a workbook. It's like a huge, thick organic chemistry.
That's a thing?
Of course.
What? Huh?
Usually, I mean, they have it every year. I mean, it was PDF last year because it was like everything was online.
Do they post it somewhere?
I hope so. No, it's either going to be online or it's going to be printed and you have to buy it. Probably from the way UVC is, probably they print it and you buy it. So because it has so much, like so many questions that it's impossible for it to not be. Yeah. So 100%. And you got to practice so much to be able to do well in organic chemistry. Like they teach you like, oh, like this is this, that's it. And then you learn actually by practicing. Their teaching is very minimal. I mean, our sessions won't be, but that's how they teach.
It's not teach.
Okay. Anyways, so let's get started. Okay. So, so we discussed that we actually have delta G naught, which is equal to delta H naught minus T delta S naught. And we discussed it briefly last time that all of these naughts doesn't mean really anything special. I mean, delta G naught has a special meaning, which we'll discuss in a second, but delta H naught and delta S naught, they're simply just delta H and delta S at a specific temperature and pressure, which is 1 atmosphere and 25 Celsius. These values change depending on what temperature and pressure is. And they have found all of these numbers for a lot of like compounds for one condition. And we are just calling it standard. So technically, this delta G is equal to delta H minus T delta S for another temperature and pressure too.
Right.
So as long as they are constant throughout this guy, it works too. Because I'm like, some of my students ask me like, wait, this is not delta G naught or this is not delta H naught. How do you just do the same thing? It's because everything is in all of the values are in the same temperature and pressure. Okay.
I see.
So, and then when we are talking about, for example, so that was like one way of finding delta G naught, and that was like how much your midterm was testing. But when we are talking about, for example, like a hypothetical reaction, which is A plus B gives C plus D with the coefficients of small a, small b, small c, small d, we have something called equilibrium constant, which is different than the next K that we study in kinetics. Totally, like they have nothing to do with each other. It's going to be K is going to be equal to the products times each other over reactants. And the coefficients will be the exponents. So D, C, A, B.
So it's like the acids and bases.
It is an acid and bases. It is. So acid bases, the Ka is a K of an acid.
Right.
So it's
This
the
is
same thing.
general K.
Yeah,
Okay.
so this is just, so this is the K of any reaction, and that was like a K of an, like, and the example that we do will be an acid-base example, so it makes more sense. Yeah.
Okay.
But,
Sounds good.
but what does it mean though? Because again, if you, a lot of people just understand this enough to plug in numbers and then you're like, okay, huh. But if you actually pay attention to the meaning of this, it makes a lot of sense. Like if you don't even have to do delta G's and stuff. I'll show you what I mean.
Okay.
The K, first of all, the end goal for any reaction is to reach the finish line. But what is the finish line? Equilibrium, which we show like this. So the rate of the backwards and forwards will be equal to each other, which we will talk about a lot in kinetics.
Right.
So this K is not just ratio of products and reactants at any time. It's the ratio of the products over reactants when you're done. When you're done. Yeah, when the reaction has reached its completion.
Reached equilibrium.
AKA equilibrium. Yeah. So when it's, most people think, oh, you mean, wait, not all of the reactants are going to consume, you're going to reach products? No. If the K of the product, I'm sorry, K of the reaction is very large, let's say, for example, like 1,000, it's not that much, but it means that, oh, when you reach the completion, you're going to have made so much products compared to reactants, it seems like nothing left. But it doesn't have to. So yeah, so what it really, but it's a ratio. For example, like when you say the K of the CH3 COOH is equal to 1.8 times 10 to the power of minus 5, what does it mean? The number is less than 1. So clearly it means what? There's more products or more reactants?
There's more reactants.
Clearly. So so the reaction is actually going to favor the reactants. And that's what makes this a very bad acid. I mean, it's a weak acid.
Right.
So that's why, yeah. So,
okay.
So you're like, okay, so sure. But you see, like, it's a ratio. It's still not going to be 100% reactants. It's going to be still like when it reaches equilibrium, you will have products, but still very negligible. But it's still a ratio. It's not 100%. So what is with all of this discussion? First of all, again, for you to understand, because a lot of conceptual questions come up about this. Really a lot. Like when we do sample midterms and stuff, you'll see a lot of questions about this. You will have like one calculation question about it, but a lot of like conceptual questions.
Yeah.
But anyways. So now you're like, okay, so sure. But what about, so is that it? Is that all the K is? Well, again, before I even relate it to the next formula, which I'm about to say, the K is, so we just said the final, when the reaction reaches, you're mostly going to have reactants. So which direction does your reaction favor then?
Going to product. It favors reactants.
It favors reactants, because if it doesn't favor reactants, how do you get the lot of reactants in there?
More, right?
Yeah. So you see, you actually just told me the direction of the reaction without even calculating delta G0.
Right.
So the delta G0, if I actually, and you'll see, it will give you a positive delta G. So it means it's non-spontaneous forward. But so you see, like, you're actually answering the question without calculating. But well, delta G0, just like you can actually solve it in this way, it can also be calculated from RT ln of K. These two values should match.
Yes.
By the way, another reminder, any formula you have R in it, in all these energy ones, it's going to be in joules. So this has to be in joules too. But I guarantee it, all of the questions that you see, the delta G is in kilojoules. To just test you to see, is this person really paying attention to the unit or not? Anyways, so let's actually test this question. Again, we're not going to even plug in the number. The ln of k of anything less than 1 is negative. So, so it's going to be negative. Obviously, temperature is positive, positive, negative. The whole thing will be positive.
Yes.
See, without even solving for the delta G, we actually predicted it just based on what the K was.
Right. Okay, that makes sense.
So awesome. So that's how you figure out. And okay, this is a very important thing, is that the delta G, the delta G naught is mostly sometimes in your text, in your slides, they mentioned the reaction is unmixed. It means that the reaction, like if we actually start the reaction with like 1 molar, 1 molar, 1 molar, 1 molar, so the reaction is like balanced. Yes. And then, so it's like, for example, like a balance, and you just let it go, where is it going to go? So that's what delta G naught predicts. You're not, they kind of, in my opinion, like in my view, delta G naught kind of tells the overall tendency of a reaction, regardless of how much products and reactants you are starting the reaction with.
Right. It matters like where it reaches equilibrium.
Like when I told you the K of the CH2COH is this, I never said, oh, you're starting it with 1 molar or 2 molar or 0.5 molar or nothing. I just told you this and you're like, oh, that's a weak acid. Why is it a weak acid? Because it favors a reactant instead of making hydronium.
Yeah.
That's the point.
Okay.
So that's how you should look at it.
Okay.
Cool. Okay. Then now here's like the interesting part. Now, so that was it. That was delta G naught. Now you know how to solve delta G naught in 2 ways.
Yes.
Now we're going to be talking about the next one, which is what do I want to say? So delta G though is actually based on something else. What is it? Well, it is actually related to something called Q.
Right.
Why am I copy pasting this? That's the interesting part. They're calculated the same way.
Right.
But if they're calculated the same way, are they the same number? Nope. It could be, but not necessarily.
Because Q is instantaneous, right?
Yeah, what it means is K is the ratio of the products over reactants at the time of equilibrium. Q is the ratio of the products over reactants at any time that you're trying to figure out the direction of the reaction.
Right. Yes.
Yeah, and also hint, again, based on my experience, it's never 100%. They never ask you to calculate the K. But when they give you a bunch of reactants, because K is kind of like an idea of a reaction. It never, first of all, you're rarely ever at the K, because you're always like trying to reach it. You're at somewhere that you're trying to reach the completion of the reaction. And when they give you the reactants and products, it's mostly you're trying to calculate a Q. Note, it's very important though. If you have a reaction that are aqueous, if the compounds are not aqueous, like let's say the A was, for example, solid or liquid or not gas. I will talk about why it can't be gas. Then you're not gonna include it. You just include like 1. Just like exactly why you didn't include water when you were doing your Ka and Kb stuff. Yeah, because it's non-aqueous. If it was a gas question, like a bunch of gases reacting together, it would be the same thing. You would just plug in, obviously when you're doing with gases, there is no concentrations. So instead of concentrations, you would have something called partial pressure, which is the total pressure, is the fraction of the total pressure that is coming from that particular gas. It's the same thing. Like there's absolutely no difference between like plugging in concentration or the partial pressure. Anyways,
right.
Okay, so now I really need you to pay attention to what I'm about to say. Again, it's another conceptual question.
Okay.
So let's say we're talking about, again, same thing. Let's say talk about the CH3COOH plus H2O making CH3COO negative plus hydronium. Beautiful. So I use this spectrum. I don't remember like where I learned it, but it's very helpful. I might have made it up. I don't know. It's pretty good for visualization.
Oh yeah, I think you showed me last time.
Oh, awesome.
Yeah, that makes a lot of sense because.
Mm-hmm. So based on this situation, like let's say we're talking about this reaction, and then we just said that again the Ka is 1.8 times 10 to the power minus 5.
Right.
So again, based on where it is, it's the K is going to be, let's say, I don't know, like it's going to be here. Obviously, it's going to be towards the reactant side than the product side. It could be further up here. That's really not the point. So the K is here, and that means that delta G naught will be greater than 0. But here becomes, again, but we still have no idea about delta G. Delta G is, again, you should look at your K as your reference point, as where you want to be, as the ratio that you're trying to get to.
Yeah.
But delta G is like the reaction that, like, the delta G can be positive or negative depending on where you are relative to the K. Are you to the right of the K or left of the K? That's the question.
Okay.
Because for example, let's say you start the reaction with, we'll use different color. Let's go crazy and say this one. So let's say my Q is here, Q1. Like I started the reaction with 50%. Again, I know that there's an exponent aspect to it, but we're just roughly speaking. So the Q1 is here. What does it mean? Does it mean I have too much products or too much reactants relative to my K?
Too much reactant. No, product.
Products, yeah.
Yeah.
So too much products, where do you think you're gonna go?
Gonna go towards the reactant.
Definitely. So the reaction is gonna go favor going backwards.
Yes.
So what does that mean? So delta G will be positive.
Right. Let's change. Okay.
So scenario 1, delta G naught was positive and delta G was positive too. Now let's talk about scenario 2. But you know what the beauty of this thing is? Again, am I talking about the same reaction, same overall reaction? If the answer is yes, the delta G never, ever, ever, delta G not ever, ever changes. You know why? Because the K is not changing.
Yeah.
So as long as we're talking about the same reaction, same K, same delta G naught, it happens to be positive in this one.
Right.
Huh.
But if it starts with more reactant.
Like, let's say 100% reactants.
Right. Then it'll go towards product.
Yeah. I mean, it goes towards products, so you can actually reach this balance. Of course, you're not going to go here, but it will go here. Exactly. Well done.
Would that be delta G is negative?
Exactly. Because you know what it is, because they actually don't explain this properly. When we say delta G is negative, the reaction is spontaneous, they're not being specific enough. By convention, they're talking about left to right all the time.
Oh.
Yeah. You're saying that, oh, the reaction is not, so that's what we said. We said the reaction is not spontaneous. It's not spontaneous from left to right. You just told me it will go left. So it's actually spontaneous from right to left.
Right. So it does happen, but they write it as it's impossible. Okay.
Because they're always assuming it goes, we're only focused on left to right.
Right.
That's what it means. Because when you say A gives B, the delta G of forward, if it is, for example, plus 20, the delta G of backward is minus 20. So if it's not spontaneous in one direction, it has to be spontaneous in the opposite direction, unless it is at equilibrium.
Okay, that makes sense.
Yeah. So that's why, like, I always, like, when I say spontaneous and non-spontaneous, I mention the direction. But I mean, that's, yeah. They kind of make a lot of assumptions in that course.
They do.
So it's
so much.
It's pretty unfair. So yeah. So okay. So now, pardon?
No, I just said I see.
Oh.
I kind of
I know, seriously, like the more you understand, it actually makes more sense. This is not a difficult course. It's one, it's a lot of information and a lot of conditions to remember. And two, the props are not the best. So
that might be the main thing.
Yeah. Okay. Wonderful. Okay, so that was delta G, and we're gonna practice again. We're gonna cover everything, and then we're gonna go back again.
Okay.
So what time it is? 30 minutes. Cool. So yeah, so let's talk about the formula. And yeah, so now that you actually, if I, again, the formula is just for numerical purposes now. So technically, again, just based on the Q and K, I can actually tell what the direction of delta G is. So if Q is equal to the K, obviously the reaction is at equilibrium. You're where you're supposed to be.
Yeah.
If the reaction, if the, so if the delta G, if the Q is greater than K, it means you have too much products and the reactants, like what you're supposed to have. So delta G is going to be positive, and you will see it's numerically, it all makes sense too. And the Q is less than K, the delta G is going to be this. Again, I'm not even bothering with spontaneous, non-spontaneous stuff, because you're like, which direction are you talking about? So now let's mention the formulas, and then we're done with technically this whole topic. And we will like do a bunch of practice questions together, so it solidifies everything. Okay, so delta G, it technically only has one formula, but we can write it in different forms. So delta G is equal to delta G naught. See, that's where the K reference come from. Plus RT ln of Q. So, so delta G, I mean, we mentioned earlier, delta G naught is equal to minus RT ln of K. So minus RT ln of K plus RT ln of Q. So you're like, well, these are the same thing. Yes, but this is the formula that I'm trying to get to, which is, I don't know, you may or may not remember this, but ln of A minus ln of B is equal to ln of A over B.
Right, so that's ratio.
So delta G happens to be equal to RT ln of Q over K. But you're like, why are you going through all of this to get to this equation? Is because I've seen questions in this course that they give you the Q and K as a ratio. Like they say we're at a point where the Q is like 1/4 of a K.
Right.
If you don't have the values, you can't use these two formulas. And that technically that would be like a more difficult question, but it's not really now because you just plug it into this. But technically all of these equations should give you the same answer. Unless you're making a calculation error. So yeah, so technically 1 and 2 and 3 actually are the same formula.
Yes.
Awesome. Any questions?
No, okay, I understand.
Awesome. Okay then, yeah, let's stop the recording because if they want to see more, you're welcome to book a session.
Yes.